So let's do some examples of this change in oxidation number method. Sitting here right in front of me are a whole bunch of irons and tins and chlorines, and I need to balance these. Now I could do an inspection sort of thing where I started putting, oh, who knows, a number down here to make it all balanced. I know it's not balanced right now because while I've got one iron here and here and a tin here and here, I've only got six chlorines here and 5 there. That's not balanced, 6 versus 5. You can just feel that the number 6 versus 5 is not something you want to mess with just sort of randomly sticking numbers into the coefficients here. So let's use the change in oxidation method. The first thing we're going to do is write down the oxidation number on each of the compounds, on each of the atoms. So that's -1 on each of the chlorines here. And then what defines the other atom is some number for the oxidation number that allows it to add up and equal 0. So because I've got 2 chlorines here, -1 each, I add that to +2 to equal 0. In this case here, this has to be +4. In this case here, this has to be +2. In this case here, this has to be +3. So I finished adding the oxidation numbers on top of the atoms. The next step is to find out what's being oxidized and what's being reduced. In this case here, my iron is going from +2 to +3. So this is a 1 electron oxidation. And there must therefore be a reduction taking place, and that's it taking place right here. This is 10 plus 4 making 10 plus 2, so this would be a 2 electron reduction. So far everything looks nice and simple. The next step is that I've got to find a way to make sure that the number of electrons going to the left and to the right are equal. Well, in this case right now, there's 1 going this way and 2 this way. I have to balance them. Well, I can balance them by finding the least common multiple. And the least common multiple is typically found by multiplying the 2 numbers together. 1 times 2 makes the number 2. Now, there are cases where that's not always the case, but usually, as long as they're not factors of each other, that's what you do. You just multiply the 2 numbers together to find the least common multiple. Now, 2 times 1 is equal to 1 times 2. And this number I'm putting out here in front is the actual coefficient that you're going to put in front of the half reaction you're dealing with. So I'm going to put a 2 here blindly in front of the irons, and I'm going to put a 1 in front of the tins, and there. I've now satisfied step 3. Step 4 and 5 are to look at the hydrogens and the oxygens if they're present and try and balance them, but there aren't any. So, according to this change in oxidation number method, I'd better have gotten the right answer here by just doing those first steps. Evidently, all I had to do to make this work was put a 2 in front of the irons. If that turns out to be true, it seems like that's pretty simple. But I don't imagine that when you first looked at this that you had any idea that that's what you should have done, any more than putting a 7 here and an 8 there would have worked. So let's see if this is working. Let's look at the mass and the charge balance. Obviously, the charge balance is there, 0, 0, 0, and 0, so the charge balance is fine. What about the mass balance? I've got 2 irons on this side. I've got 2 irons on that side. I've got 1 tin on this side and 1 tin on that side, but that was never my problem. My problem was the chlorines. Let's see how this is doing. There's 4 chlorines there, and 4 chlorines there makes 8. I have to have a drum roll here. I better see 8 chlorines over here, or this failed me. Well, 2 plus 2 times 3, 6. That's 8 chlorines, 8 and 8. They cancel. This is, in fact, a balanced redox reaction. I've used my change in oxidation number method to basically balance this all on a single line. I didn't have to write stuff down all over the place. I was able to balance it right where you see it.